In business analytics, performance is often evaluated by summarizing thousands of data points into a single central average. To see where that logic breaks, we need to look at how two identical averages can hide two different realities. Consider two different Indian companies. Both report an identical average monthly revenue of 50 lakh rupees. Company A hits that target reliably, with minor fluctuations. Company B achieves the same average, but its actual monthly revenue swings between 10 lakhs and 90 lakhs. The identical 50 lakh average masks Company B's volatility. An investor looking only at the central tendency would view these two companies as identical, missing the severe unpredictability embedded in Company B's cash flow. This illustrates why statisticians use the average of the second order, formerly known as dispersion. If a standard average locates the center of the data, dispersion measures the internal scatter of the individual data points around that center. Within the Indian economic landscape, dispersion serves as the mathematical proxy for risk. It quantifies exactly how much the central average should be distrusted. The Securities and Exchange Board of India uses dispersion to categorize risk levels of mutual funds. The Reserve Bank monitors the dispersion of price changes across sectors to formulate inflation policy. In manufacturing, it dictates whether an entire assembly line passes quality control. Because an average only provides the middle of a dataset, a secondary toolkit is necessary to quantify how representative that middle actually is. We are going to construct that mathematical toolkit. We will move from crude early estimation methods to the standard for measuring dispersion. These tools fall into two distinct categories: absolute measures and relative measures. Absolute measures calculate risk in the exact original units of the data. If you are analyzing a portfolio in rupees or a crop yield in kilograms, the absolute dispersion is expressed in those exact same rupees or kilograms. Mastering risk assessment involves understanding the mechanical flaws these equations were designed to overcome, rather than simply memorizing the formulas. The simplest absolute measure is the range. You calculate it by subtracting the smallest value in a dataset from the largest value. This is frequently deployed in the stock market. When the National Stock Exchange reports a 52-week high and low for an equity, it is providing the mathematical range of that asset's trading price. The flaw of the range is its hypersensitivity. A single freak outlier, one momentary market crash, warps the entire calculation. It also ignores the distribution of the data points sitting between those two extremes. To fix this outlier sensitivity, statisticians developed quartile deviation. This diagram illustrates a standard box plot. Notice the blue shaded section labeled interquartile range. Quartile deviation works by isolating this middle 50% of the data between the lower quartile Q1 and upper quartile Q3, while cleanly severing the extreme variables on either end. This makes quartile deviation effective for Indian socioeconomic surveys. When analyzing household income, omitting the lowest and highest 25% prevents a few ultra-rich billionaires from distorting the economic reality of the middle class. But quartile deviation has a structural limitation. By ignoring the top and bottom quarters of the dataset, it explicitly discards half of the available data. Quartile deviation successfully filters out anomalies, but discarding half a dataset leaves us without a comprehensive measure of total variance. We need an equation that accounts for every single observation. The challenge is to build a measure that tracks the exact distance of every single point from the mean without throwing any data away. If you measure the raw distance of each data point from the mean and add them together, you trigger the cancellation problem. Positive deviations above the mean and negative deviations below perfectly cancel each other out, leaving a sum of 0. The mathematical fix is to square every deviation. Squaring the distances converts all negative values into positive numbers, preventing them from canceling out the positive deviations. Averaging these squared distances gives us the variance. Finally, by taking the square root of that variance, we return the metric back to the original units of the data. This complete process produces the standard deviation. The squaring mechanism provides the mathematical foundation of this equation. By squaring the distances, the formula penalizes larger variations. A data point that misses the mean by 10 incurs a penalty of 100, forcing the final metric to reflect extreme risk. Because it accounts for every data point and weights volatility through a penalty system, standard deviation has become the mandatory benchmark for measuring financial risk. This chart shows the normal distribution curve. Under SEBI regulations, mutual funds are required to disclose their standard deviation to quantify historical volatility. The sigma symbols on the x-axis represent these standard deviation intervals. By mapping these intervals, analysts can see the exact percentage distribution of past performance. This allows them to project what percentage of a fund's future returns will fall within acceptable risk boundaries. In modern corporate environments, analysts bypass the manual arithmetic entirely using Excel automation. The syntax requires precision. You use equal stdev.p when calculating the total population of a dataset and equal stdev.s when evaluating an audit sample. Standard deviation perfects absolute risk measurement by utilizing every observation and penalizing instability, producing a metric that captures the magnitude of volatility. Standard deviation has a critical limitation. Absolute measures fail when comparing datasets of different scales. Consider an analyst evaluating the volatility of two assets. MRF stock, priced around 100,000 rupees, has a standard deviation of 100 rupees. Tata Motors, priced at 900 rupees, has a standard deviation of 40 rupees. At first glance, Tata's 40 rupee deviation looks lower than MRF's 100 rupee swing, but comparing these absolute values ignores the difference in the underlying stock prices. The solution is to use relative measures. These are coefficients designed to strip away the original units, erasing the rupees entirely, to provide a pure unit-less percentage. The primary tool for this type of relative comparison is the coefficient of variation, or CV. The CV formula is calculated by dividing the standard deviation by the mean and multiplying the result by 100. Applying the CV formula normalizes the data. Dividing MRF's 100 rupee deviation by its price yields a CV of less than 0.1%. Dividing Tata's 40 rupee deviation by 900 yields a CV of roughly 4.4%. Tata Motors is actually far more volatile relative to its price. Because Excel lacks a native CV function, business analysts construct it manually. You divide the sample standard deviation function by the average function and multiply by 100. Absolute measures deceive when scales mismatch. Normalization through the coefficient of variation is the only objective method to compare consistency across the diverse asset classes of the Indian economy. This logic extends to corporate operations, where the coefficient of variation becomes the consistency test. Human resource managers use it to evaluate sales executives. If an executive in Mumbai has a target of 1 crore and an executive in Pune has a target of 20 lakhs, their absolute sales deviations cannot be compared. Calculating the coefficient of variation normalizes their performance data. The executive with the lower CV percentage provides the more reliable, predictable output to the firm, regardless of their total sales volume. This metric also dictates quality control in the industrial sector. In automated manufacturing, the physical consistency of components is critical. Factories must maintain an ultra-low relative dispersion rate in the dimensions of their parts. High dispersion means components won't fit together on the assembly line, leading to product rejection and the loss of ISO quality certifications. Whether evaluating financial portfolios, sales teams, or factory outputs, relative dispersion transforms raw scatter into a universal index of operational reliability. We have moved from the simplicity of the arithmetic mean to the precise tools of dispersion. To apply this in practice, analysts use a strategic decision matrix. Deploy an absolute measure, like standard deviation, when you are analyzing a single dataset and need to manage the magnitude of risk in its original units, like setting a strict rupee stop-loss limit on a trade. Deploy a relative measure, like the coefficient of variation, when you are comparing stability across differing economic scales or separate asset classes. For statutory auditors determining sample sizes, SEBI regulators categorizing mutual funds, and corporate managers securing supply chains, dispersion is the foundational metric of due diligence. Ignoring internal variance and making strategic decisions based solely on central averages leaves long-term risk management highly vulnerable. True mastery of business analytics requires moving past the illusion of central stability. By utilizing dispersion, analysts anchor every operational and financial decision in the mathematical reality of risk.